For the introduction. Can everyone hear me?
Yeah. Yes.
Yes.
Thank you. All right. Hello, everyone from Santa Cruz. I shall be talking about the end of the life cycle of galaxies, or how do galaxies die. So as you can guess from the title here, so winds clearly have some sort of connection here, and that will be clearer as I move through the talk. Okay, so when I say how do galaxies die, what do I mean? So on the left, here is a picture of a spiral galaxy with visible spiral arms, and they have lots and lots of stars in them. And if you look closely, you can see a slightly bluish color coming from them. So this blue color signifies that there are lots of young and hot stars that reside there. But the stars will eventually burn themselves out and they will turn off. And then they need to be replaced by new young stars. Now, this phenomena of formation of new stars is quantified by something called the star formation rate, or SFR in general. Now, the star formation rate can be high, just as in the case of spirals, where there are lots of new stars that are forming. But for some galaxies, star formation rate can be low. And then you get something like this. So you get an old galaxy. So these are generally elliptical or spheroidal in shape. So no new stars are forming. So there is no young or hot stars shining in blue. And all the stars are pretty old. So the stellar population is pretty old. And these are red in color. So that is when a galaxy is considered to be to be dead. But the question was how? So how exactly do the galaxies die? That means how do these young star-forming galaxies turn into these red and dead ellipticals? Or what causes the star formation rate to diminish? You may think that, well, this is a very simple answer. Well, with time, the galaxy might just run out of fuel to form new stars. So pretty much like your car, when it runs out of fuel, it will just not run anymore. But turns out the answer is not that simple. Astronomers actually detect lots and lots of fuel for star formation in old galaxies. And when I say fuel, I mean gas and dust. And this gas and dust comes from a variety of sources like stellar mass loss, mergers, accretion events, etc. So in general, they do have fuel, and that is not the main reason for this. So there is another thing here. So this plot shows the number of galaxies versus time. So as you move from the right side of the plot towards the left, you are moving towards present time. And the red points, so you should focus especially on the red points. The red points show the change in the number of red galaxies with time. And I can clearly see that the number of red galaxies has been increasing very steeply towards present time. So what does that mean? That means that there is a lot of blue star-forming spirals which are changing to red and dead galaxies. And there is so much change that it cannot be explained by just a mere gradual exhaustion of fuel. So you need something else. To answer the question, we have to realize that a galaxy is not just a collection of stars. So there is more. So in the center of every galaxy, there is a giant supermassive black hole that resides. And in some cases, they are quiet, kind of like our own Milky Way galaxy. They just don't do much. Or in some other cases, they can be really active. And in those cases, they are called the active galactic nuclei, or AGN in short. So here, the black hole accretes lots and lots of gas and dust from the surroundings, and they give off radiation and matter in the form of jets or outflows or winds. Now, in addition to a black hole at the center, galaxy also has other things. For example, a galaxy has lots of gaseous clouds floating around in the space in between the stars. So these are called interstellar medium, or the ISM in short. There are also quite a lot of gas just outside this stellar disk of the galaxy, extending all the way up to the boundary of the halo. And this region is generally called the circumgalactic medium, or the CGM. And there is a constant interplay or interaction that is happening between the ISM and the CGM. And these are characterized by different activities, like there can be accretion of gas. So gas might be accreted from the CGM or even outwards into the galaxy, into the ISM. There can be outflows where gas can just be ejected from the center of the galaxy or somewhere here outwards from the galaxy. Or there can also be some sort of recycling. It's kind of like a fountain. So some of the gas may be thrown out, but they can come back down. And all these three mechanisms are very important elements of the galaxy evolution, and these are very deeply connected with activities like star formation inside the galaxy. Okay, so let us talk about outflows. So back in 1998, there were two seminal papers by Megorian and Silk and Rees, and they proposed for the first time something called the AGN feedback. So we already know what AGN is, so this looks something like that. So what AGN feedback proposed is that the AGN, the AGN jets or outflows, what they do is they push out the gas away from the center, and they can also inject energy to the surrounding gas and dust. And both these conditions are very unfavorable for the formation of stars because you need cold, dense gas available nearby to form stars. Now, so you can either push the gas away or you can heat it up. Either way, you will just stop forming stars. You will not form stars as much as you were previously. So this was AGN feedback. And about 15 years or so later, this picture was taken, and it clearly shows that what these guys were talking about. So this big panel is a combined image of three different images taken in three different wavelengths, which are shown in the side panels: radio, visible, and X-ray of the same galaxy cluster. So in the center, we can see that there is an AGN, which is most bright in radio, but these are also visible as a bright spot in the middle in optical and X-ray. It has radio jets, which is visible in radio. And these radio jets are clearing out cavities and creating pockets in the gas, which are seen in the X-ray image of the galaxy cluster. And this galaxy cluster is also shown to have a lesser amount of star formation in them. So this is like a perfect example of AGN feedback. Now, not just this example, there are a few others that show similar things. And in all of them, you can see either bubbles or jets or winds or outflows blown out from the center. So these are all good examples of AGN feedback. So then is this the answer that we were looking for? Is this the answer for the suppression of star formation? But there is one thing to note here. If you read the different levels here, these are all these examples are either galaxy cluster or galaxy group, or if there is a radio galaxy here. So these are all either large scale objects or very rare species. So these are not typical elliptical galaxies. So we haven't quite found feedback signatures in typical galaxies yet. So now the question is more like this. So what causes the star formation rate to diminish in typical elliptical red-ended galaxies? Maybe AGN feedback like that, which I was showing previously. Maybe not, maybe a smaller version of feedback. So this has been widely discussed in the literature, and we expect this feedback happening in the ellipticals to be much smaller and less exotic than what I was showing before. And probably these feedback signatures happen much more frequently to explain the galaxy population at large, because there are so many elliptical galaxies, you need to explain all of them. They should also have an active AGN in the center, of course, but maybe less luminous than the giant radio galaxies that I was showing you. And finally, they should also show winds or outflows or jets that can actually perform the feedback action. So these are sometimes called the maintenance mode or radio mode feedback. But again, these are just proposed theories. We still need to observe these characteristics in real data in ellipticals to actually prove this. So this brings me to the outline slide. I have already given a background of the AGN feedback. Now I'll very briefly talk about some of the observational tools that we could use to try to observe some of the signatures that I was talking about. And then I'll move on to my own research. Oh, hello.
I think I can hear you. Can everyone else hear?
Yeah, I can hear you too.
Yeah,
Yes,
that's
yes,
fine.
yes. We
That's
can hear
fine
you.
then.
Yeah, I hear
Yes,
okay.
yes, fine.
Okay, great. You can go ahead then. Yeah.
Okay. Um, Okay, so as I was saying that after talking about some of the observation tools, I'll go to my own research. So I'll introduce a population of quiescent galaxies, which show potential signatures of feedback called the red geysers. And I'll ask three questions to these galaxies. Do they have an active AGN in the center? Do they show outflows? Or how are the active AGNs fueled? Kind of like similar question to the ones I was showing you in the previous slides. And we want to understand what is actually going on in these galaxies. Now, I'll come back to these questions from time to time. Okay, so there are two main observation probes. We all know that. One is imaging, when you just directly take a picture of the galaxy with a telescope. And that can be done in different wavelengths depending on the telescope you are using. So I showed mostly images in my previous slides to kind of motivate the feedback. But again, kind of reiterating what I was saying before, that all these examples are very extreme cases. So these are either large scale or these are very bright clusters. So these are gigantic. And hence it's pretty obvious what is going on just from an image. But now what we are looking for is fainter signatures within ellipticals. So we would probably need much more than just an image to tease out those signatures. And that's what spectroscopy gives you. So what you do is you put a slit in front of the target, and then you put a prism or any other dispersive element to kind of split the light into its different wavelength constituents. And you get a spectra that looks something like this. And in order to illustrate the power of spectroscopy, let's look at this diagram. So if we put a prism in front of some object that emits in black body, kind of like a star, we get a continuum spectra. Now, if there is, let's say there is a cloud of cooler gas in front of that star, and so some of the photons releasing from the star would get absorbed by this cloud of cooler gas. So what you eventually observe in the spectra is a bunch of absorption lines at specific wavelengths on top of the continuum spectra. And then this cloud, let's say this cloud kind of goes more nearer to the star, and it has some sort of like other sources nearby. So this cloud can get heated up by the radiation from the star or some other source. So then this cloud would emit a radiation by itself. So it will emit emission line spectrum. So this is an example of a spectra. And this widespread, this shape, overall shape of the spectra is what we call the continuum. And that is what I was talking about here, that comes totally from the star. Now, in addition to the continuum, there are other features in the spectra. So there is an absorption line here, which is visible, which comes, as I said, which comes mostly from the cooler gas. And there are a bunch of emission lines here, which comes from the warm to hot gas. So you can see that you can basically detach the contribution of the star and the gas in the galaxies by just using different tracers or different signatures in the spectra. And not only that, you get a ton of other information like ionization, velocity, dispersion, flux, etc., etc. So this is where the spectroscopy really comes in handy. Okay, so there are several ways to actually get this spectra. So you can have slit spectra, where you put one slit on top of the galaxy and you get an integrated spectra from the whole galaxy. So you basically get some global properties of the galaxy. And you cannot tell, but in this case, you cannot tell what is happening in the inner region of the galaxy versus the outer region. You just get one spectra here, and that's all you get. But then you can go one step forward. So let's say the galaxy is a little bit closer to you. So it's slightly bigger on the sky. So then you can place a slit on the galaxy, and you can actually extract multiple spectra along the different spatial pixels here. So you can extract spatially resolved information along the slit. And then you can put multiple slit on the same galaxy, And thus you can sample the whole galaxy and you get spatially resolved information, which is a lot more useful than this case. But as you can imagine, it's if you want to do observation like this, you would need a lot of slits and a lot of observation times. And that might not be feasible for a whole bunch of galaxies. So next comes the integral field spectroscopy, or what is called IFU spectroscopy. So these are basically bundles of optical fibers, which are packed together in a closed shape, like something like a hexagon here. And these are connected to the telescope. So what you get from this spectra, so what you get from here is a spectra from each of those spatial pixels, or we call it spaxels. So you get a spectra from here, from here, from here, from all over the galaxy. And let's say you're interested in something like flux or velocity. So what you can do is you can extract the spectra from each of these spaxels. You can measure the flux from each of those spectra, and you get a 2D map of the flux or whatever you are interested in. So that will basically show you how the flux in the galaxy is distributed all over in the entire region of the galaxy. For example, here you can kind of see the spiral arms and how the flux is distributed. So I'll be showing a lot of these 2D maps all over my talk, and these are really useful to kind of see what is happening in the entire galaxy. There have been several major surveys that have given us quite a lot of data. The two surveys that I actually want to mention is the Sloan Digital Sky Survey, or SDSS, which has been particularly groundbreaking, which has provided slit spectra for hundreds of thousands of galaxies. But I mostly work on MANGA, which is actually a survey. It's a survey of SDSS. It's a part of SDSS. But it produced integral field spectroscopy that gives us spatially resolved information on several thousand galaxies. Okay, so now let's go to the red geysers. So when I say red geysers, you might expect to see something like this, but it actually looks more like this on the right. So here, what I am showing you is a 2D spatially resolved H alpha equivalent width map. So that's a lot of information. So H equivalent width is basically like flux. So it's a flux coming out from a specific emission line. So here the emission line is H alpha. So you can treat this as a flux. And here what this map is showing you is basically what warm ionized gas is doing in this galaxy. And these maps clearly show this bisymmetric or biconical feature, which is one of the main characteristic feature of these red geysers. And not just one, we actually get a ton of these examples. I think right now we have more than 160, 150, 160 of them. So if you look at the images right next to it, these are all optical images taken from SDSS. They all look like perfectly elliptical galaxies with no peculiarity in them. But all of them, all of their warm ionized gas maps, which are traced by H alpha, they show this extended biconical or bisymmetric feature, whatever you call it, throughout the galaxy. So let's first talk about why do we call them red geyser. So first of all, they have very low star formation rate. So this is a plot of star formation rate versus stellar mass. And the red geysers are shown by red points here, and they all lie in the lower part of the plots. That means very few stars are forming in this galaxy. Now let's look at the stellar population, or what's the current age of the stars. So for that, we look at the spectra. So the first observation is this spectra does not have a whole lot of emission lines in them. And the second observation is the spectra kind of goes, they have a steep slope near the blue end. So they kind of goes down here. So both these features indicate that they are filled with old stars. So this galaxy is very red. And on top of that, if we look at any of this H alpha equivalent width map, it looks like a geyser or a fountain is kind of ejecting material away from the center. So that's why we decided to call it red geysers. And as I mentioned, this kind of looks like some sort of a fountain or wind driven out centrally. So we wanted to see what exactly is happening in this. So we decided to look for an AGN in the center to give a clue of what's happening. So we are hunting for low luminosity radio AGNs here. So the first point is that they are not super bright like quasars or radio galaxies that I was showing you before. So these are pretty faint, so they should be hard to find. So we looked at the VLA first survey. So this gives us radio data at a frequency of 1.4 gigahertz, wavelength of 20 centimeters. The sensitivity is 1 millijansky. Now, the greatest advantage of this survey is that there is almost 100% overlap in terms of sky coverage between FIRST and SDSS manga. So all the galaxies in my sample actually have data in the FIRST. So now what we want to do is we want to compare the radio emission coming from the red geysers to something. So for that, we set up a control sample. So the control sample is similar to the red geysers in terms of global properties like mass, color, shape, eccentricity, redshift, etc. But they differ in local properties like the bisymmetric feature that the red geysers show, or there are also other features that I'm not mentioning right now. So it's kind of like we want to compare apples to apples, but we want to compare between different varieties of apples to see which one is better. So now what we want to do is we want to check how many of these red geysers are radio detected versus how many of these control galaxies are radio detected. And we found that there was a higher radio detection rate in the red geysers compared to the control, which means that there is a higher probability of getting a radio emission from the red geysers compared to other quiescent or elliptical galaxies, which are not red geysers. Now this is exciting. But again, as I mentioned, we are looking for low luminosity AGNs, plus the sensitivity of 1 millijansky, it's not that great. So there are many faint signatures which are just below this detection threshold that we are missing out. So for that, to get around that, what we do is we stack our signals, because stacking reduces the noise and then it brings out the obvious signals or the patterns. So we took all the red geysers, we stacked them together, and this is the stacked radio image that we got. And similarly, we took all the control sample, we stacked them together, and this is the image that we got. And if you just look at this image, you compare these two images, this one clearly has more signal than the control. And this plot is just a technical way of saying the same thing. So the y-axis gives you the stacked radio flux, and the x-axis gives you the different samples and subsamples we tried this stacking exercise on. So we can ignore that for the time being, but we see that in all the cases, the red point that signify the stacked red geyser, these always lie higher up than the control sample, which is shown by blue. So the red geyser stacks always show an enhanced radio emission compared to the control sample. And we of course ran tests, and we looked whether this radio emission can come from other source, and we confirmed that these are coming from low luminosity AGNs at the center. And I wanted to point out that from this plot itself, there are a bunch of other scientific questions that can be answered. For example, what's the average luminosity of the AGNs that reside in these red geysers? How many of them are radio bright? What is the radio energy? Is the radio energy enough to drive winds, etc., etc., etc. So there are many questions that can be answered, and those are very important to kind of know what is going on in these galaxies. Okay, so now we have evidence for the presence of AGNs. So the next automatic question is, well, do they have winds? Or if they do, how do you know these are actually winds and not anything else? So to test that, we look at the kinematics, or the velocity structures. So here, these two maps are the maps of velocity. So this map on the right is the stellar velocity field. So this basically shows how the stars are moving in the galaxy. And these are extracted from the continuum that I showed you before in a spectrum. And this is the spatially resolved velocity of the ionized gas. And we have used H alpha line as the tracer, similar to what I was showing you in the previous maps. Now, in order to get this pattern of ionized gas velocity, there can be two possibilities that can actually explain this sort of like velocity, that can produce this sort of velocity field. So one is if the gas is rotating. So if the gas cloud is rotating like this in this direction, in and out of the plane, this can show up something like that in the velocity field. Or if the gas clouds are moving radially outward, kind of like a wind, that also can produce a velocity field, something like that. Now, to kind of remind you, we are actually trying to prove that these galaxies have wind. So we actually think this is the right scenario. But to prove that, we first have to disprove this one. So let's first talk about the rotation hypothesis. So if are the gas clouds rotating? So let's first assume that these are indeed rotating. So if they are rotating, so kind of matching with this figure, they will have to rotate in this direction. Again, going in and out, because this part is blue shifted coming towards you, and this part is red shifted coming away from you. So they are rotating in this direction, and the stars, they are moving in this direction. And they have a clear misalignment in the plane or the orbit of rotation. And this is another important characteristic feature of the red geysers that is seen in all the red geysers. And this is weird because in any rotating disk galaxies that you see, the gas and the stars, they generally always rotate together in the same plane. But here they are clearly decoupled. So in normal conditions, these cannot remain in equilibrium if the gas clouds are rotating. So this misalignment kind of causes a lot of problems in keeping them in equilibrium under normal conditions. The second point is the actual values of the velocity. So here in this plot shows the velocity versus distance. And in this plot, the point with error bars show the actual values data extracted from this velocity field, but along the major axis. So you basically take points along the major axis of this 2D velocity field and you plot it here. And then we try to fit them with different rotating disk models. So the different models are, some of the models are shown here by the different lines. And the closest model, the closest that we could go to the data is that orange model. And this is the model where we assume a very highly inclined disk. So there is a very highly inclined disk, almost edge on, eye is almost 90 degrees. That's the closest we could go to the data. But even then, it's quite a bad fit to the data, as you can clearly see that it has like a weird shape, plus it's a lot of excess compared to the model. Plus, we do not see any highly inclined edge on disk in our galaxy image. So all those images look like perfectly elliptical galaxies. So in summary, the data is not fit by models. And if you look at the velocity values of gas, some of them are pretty high. They go upward of 250 to 300 kilometers per second. And a fraction of those velocities even reaches beyond the escape velocity. So this kind of combined, all these combined evidences rule out the rotating hypothesis. So now let's test the outflowing theory. So we have a toy wind model, which I can talk about in detail later, but it is basically a bicone geometry. It is filled with particles in it that resembles the gas clouds. And all those particles are assumed to have a constant radially outflowing velocity vector. And we have assumed some density. And the inclination, position, angle, radius, these are all tweakable parameters. So we can tweak them and we can construct our model. And then we project it along the line of sight. And that's the model velocity field that we get from the simple wind model. So just kind of reminding, this is a very simplistic wind model. There is no ionization or any other realistic features that is incorporated here. It's just the velocity field is radially outflowing. And the model velocity field looks something like this. And this is the observed velocity field of one of the red geyser, which we tried to match with. And it seems like just by using a very simple wind model, you can still qualitatively reproduce many of the features that you see in the data. There are other matches as well. There are other things that we also matched, like the dispersion, the misalignment, and all of them agree when we apply this wind model. So that's a pretty good start. Now we want to kind of look into a more detailed kinematics or more detailed velocity structure. So we followed up some of our objects with higher spectral resolution data. We use Keck data for this particular study. So this plot on the left shows a cartoon of a 3D bicone geometry like before. It's full of particles or gas clouds like before, and all these gas clouds are moving radially outward. And since they represent warm clouds, so all of them emit an emission spectrum. Now the observer, let's say he's on the right. So he will see everything projected along the line of sight. So whatever he sees, he will project it along the line of sight. You cannot deep project anything along the Z direction. So he will see everything. So due to this projection along the line of sight and the radially outflowing motion, they kind of, these two conditions, they come together and they produce this asymmetric emission line. So this geometry, this outflowing nature and the projection, they should produce an asymmetric emission line. And not only that, this asymmetry would switch from one side of the galaxy to the other. So on the blue shifted part of the galaxy, there would be a red wing. And on the red shifted part of the galaxy, there should be a blue wing with a perfectly symmetrical spectra near the center. And this comes out naturally from the geometry, as I said. So this is the hypothesis. So we wanted to look for the signatures in the actual data. So we followed up with Keck data. So we put our Keck slit on top of our galaxy, and we extracted spatially resolved spectra along each of these pixels here. And the spectra are shown here. So the spectra from going from blue to the red are shown on top of each other. So the observation from this pixel is shown in the bottom left panel. The observation from this pixel, from the uppermost pixel, is shown in the topmost panel, and everything in between goes everything in between. The data is color coded by the velocity, and they are shifted to kind of offset to the same peak. And these, the spectra is shown along the H alpha and N2 region. So this is the H alpha emission line, this is the N2 emission line. So the only thing to notice in this plot is that these emission lines are, they are actually asymmetric. And if you look closely, in the blue side of the spectra, they have an asymmetry to the, in this direction, similar to what we predicted. And in the red side of the spectrum, they have an asymmetry on the other direction, as we predicted. And at the center, you see a perfectly symmetrical emission line that corresponds to the center here. So this systematic asymmetry in emission line is great, because this is what we predicted from this geometry, and you cannot reproduce this kind of change in asymmetry with any other configuration. So we are confident that these are winds at this point. Now, we have already talked about how that they have an active AGN in the center, red geysers, they show outflows or winds. So finally, the final question that we are going to ask is how is this cycle completed? So how are the AGNs itself, how are they fueled, and how do the entire gas circulation takes place? Now, to look at that, we now look at the absorption lines. So remember, I explained that the absorption lines basically happens when there is a cloud of cooler gas in between the star and the observer. So we are looking for cool neutral gas clouds, much cooler than the warm ionized gas that I was showing you previously with H alpha. So the stellar and the cool gas signature, these are both embedded into these absorption lines here. So this is the sodium doublet feature, and this is the magnesium lines. And they have both the stellar and the gaseous component, so we can subtract out the stellar component using stellar templates, using different sorts of modeling. And we can extract only the cool neutral gas cloud contribution. And this is shown for the 4 different galaxies. So here, first of all, the first observation is that there are lots of cool neutral gas, which is sitting around in the galaxy. And the second observation is that they are all kind of lopsided. They are seen to connect the center, and they just like, you know, as if coming in from one side. And we used the sodium doublet line to trace this cool neutral gas cloud. Now let's just place this cool neutral gas maps alongside the warm ionized gas maps. So this is traced by H alpha, as I was showing you earlier, and this is the ones which are traced by sodium D. The first thing is that there are lots of gas present in these galaxies, both in the cool component and the warm component. So these are just sitting around to form stars, but these are not forming any stars. The star formation rate observed in these galaxies is very low. And the other observation is that, as you can see, that these two galaxies, so if you just compare panel by panel, the warm and the cool gas, these are spatially offset from each other. So where these guys are lying, these guys are not here. So this is like completely complementary or offset from each other. So what does this tell you? This tells you that they must be tracing different activities in galaxies. And we already know what the warm ionized gas is doing. We just proved that these are winds or ionized gas outflows. But we don't know what this component is doing. So in order to understand that, we again have to kind of look into the velocity and the kinematics of these galaxies. Not going into the detail, but there is one thing that I do want to point out, that let's say I'm the observer here looking down at the galaxy. So this is the galaxy. And the absorption line happens when the observer and the galaxy has a cool gas clouds in between. So this is the gas cloud that is, let's say, that's causing the emission line. And if you see a redshift in that gas cloud, that means if the gas cloud is moving further away from you, that actually means that this gas cloud is moving inward towards the galaxy. So redshift means inflow. That's all you need to know about this from this. So this is actually called down the barrel measurement. So this is kind of this is how people generally measure and interpret data in absorption lines. And we went and looked at the spectra of sodium D of red geysers. We stacked them together. We looked at separate galaxies. We looked at the spatially resolved spectra coming from different parts of the galaxy. And we saw a very strong redshift coming from the red geysers, but not so much from the control sample. We don't see any signatures of redshift in the control sample, but we see a significant amount of redshift in the red geysers. I'm not going into the detail of this talk. This is technical jargon, but it seems like the cloud of cooler gas is actually inflowing in the red geysers. So that, and I already showed you the map of those cooler clouds, and they all look like they were kind of connecting the center, and they have like a lopsided or one-sided feature. So we can kind of connect the dots, and we can say that maybe this cool neutral clouds, what they're doing is they are coming inward into the galaxy, and they're fueling the central active galactic nuclei in the center. So if this actually holds true, so this is still work in progress, but if this actually still holds true, that will kind of give a very nice picture. So we have proved that these galaxies have a radio mode AGN in the center. So this AGN is kind of driving away hot ionized wind, warm ionized wind, which is outflowing, which is going upward. But there's these outgoing clouds, they cannot escape the galaxy. They just floats around for a while. And then they eventually cool down. And this cool gas, they just rain down in the galaxy. They come back down, and they come as infalling gas, and they make their way into the center of the galaxy, and they fuel the AGN in the center. And that's how the AGN remains active, and then they drive winds again. So this is kind of completing the cycle, gas cycle in these galaxies. Okay, so in conclusion, it seems like in going from blue star forming spirals to a red-ended elliptical, there is a red geyser somewhere. We think that these red geysers, these are a phase. So these geyser-like signatures, this is a phase. It turns off and on depending on the AGN in the center, on the strength of the luminosity of the AGN, depending on the gas circulation or the abundance of gas, how much gas there is nearby, or the different time scales that comes into play. And well, do these galaxies show signatures of feedback? Well, we do think we are starting to see initial signatures of that. But again, there are lots of work that needs to be done so that we can say confidently that yes, these galaxies do show signatures of feedback. And I have put like 3 little plots here to answer each of those 3 questions that I asked before. And in case you didn't quite get what I was talking about in my entire talk, this meme just sums it up. Yeah, and with that, I'll end and take questions.
Thank you for the great talk, Namrata. And so now we will be taking questions, and you can go ahead and raise your hand. And before that, please go ahead and raise your hand. We had a question during the talk in the chat, so I'm going to read out that for you. So the question is from Ashif. He asks that, can we think outflows like some kind of diffusion? Are these outflows isotropic outside AGN, and how are they created?
Okay, thank you for the question. So did you say isotropic? Can I actually look at the question?
Yeah, I think if you go to the chat and
Okay.
you scroll
So the
2 to
question
3
is, can we
messages above.
think outflows like some kind of diffusion? Are these outflows isotropic outside AGN? How do they get created? So first of all, these outflows are not isotropic. So these are just winds which are kind of driven out by the AGN. And whatever I was showing here in the emission and absorption line, those are just basically just tracing the wind signatures. How do they create it? That's a good question. So so the AGN, so as I said, though, we know that the AGN is basically a black hole which accretes a lot of gas, and then it ejects stuff from the center. So what I am telling you here is a low luminosity version of that. So that's why I keep saying winds and outflows interchangeably. Yeah, so they are basically just, these are radiation that are ejected from this AGN. How exactly they get created, I think that's still under investigation. These are definitely not isotropic. These are seen along the along the polar region, like along the 2 sides, as I was showing you in the figure here. Yeah, I don't know if that answers the questions, but.
Okay, so moving on, I think Ogniboda has a question. So Ogniboda, please go ahead and unmute yourself.
Hi, Namrata. Nice talk. I have a very naive question. I think I missed it somewhere in your talk. So how exactly did you come to the conclusion that your red geysers have a low luminosity AGN at their centers? So did you do some spectral analysis there or something?
We did not do spectral analysis. We don't have, so these are all actually continuum emission. So what we did was we basically, we took the luminosities and we stacked them from different samples.
Right.
So the red geysers versus control. And we, what we did is again, we bootstrapped so that we kind of take all sorts of control sample here. We do not bias it to a single control sample. And we look at the luminosity. And then we have, so there can be like, there can be 3 or 4 sources of the radio, right? So there can be star formation. Star formation sometimes gives off radio emission. There can be supernova that can give off radio emission, and there can be AGNs, right? And within that luminosity range that we were seeing. So you have to consider the luminosity. So the first thing is that these galaxies do not contain star formation. They do not show any star formation, but we did some calculation that if we assume that all this radio emission is coming from a star forming blob, then what would be the expected star formation there? And that star formation is very high. So in order to produce this kind of luminosity here, you would have to have like 10 solar mass per year star formation rate. And we see like 10 to the power minus 4 solar mass per year star formation rate. And regarding like supernova, so we controlled for a few factors when you set up the control sample, like mass, like color, and other factors. And you would not see a sudden increase in supernova in this sample compared to this sample, because we controlled for those mass and the age. So you'd not see a sudden increase in supernova in red geysers out of nowhere. So the only thing that were left is the low luminosity radio AGNs.
Okay, okay. So the amount of increase is just 2-3 times, right? From, I
Yes,
guess.
yes. So
Okay,
the
and that's
right.
very significant.
Yeah, so it's like 3 times higher. The flux is 3 times higher. And we actually like
Okay.
did other stuff. Like we took out the ones which are radio detected so that we are not biased by like only the radio bright ones, because there can be also AGNs here, you know, but like you are looking at like the comparison, like how many AGNs are here versus how many are here. Something like
Okay, okay, okay. Thanks.
Um, Great. And now we can move to RC sir's question.
Hi, Namrata, can you hear me?
yeah.
Yeah, so I guess I have many questions, but I'll talk to you later.
Okay.
Um,
Sir, your
this
sound
kind
is very faint.
Yeah, sir, your sound is very faint.
Can you hear me now?
Yeah.
Yes.
Okay, so in this kind of discussion about AGN feedback, we
Yeah.
are usually so excited to find the clues
Yeah,
and put them in the right spatial
exactly.
sort of locations and put them in the right statistical significance that
Yeah.
sometimes we ignore the temporal aspect. You mentioned that there are time scales
Yes,
involved and
yeah.
so on.
There are time scale involved.
Yeah.
Yes.
So I'd like to ask you something about the temporal aspect,
Yeah.
which is that, I mean, if this picture is really true, then some of the time scales has to also match. For
Right.
example, how long does it take for the cool gas to inflow, or how long the outflow will take to, sort of move out all the gas reservoir,
Mhm.
or, these red geysers, are
Right.
there red shifts at the right redshift range and so on. So can you comment on any one or more of those?
So, so the first question I'll address, I guess, is the gas reservoir that you were talking about. So, so there is a duty cycle, right? So of every single thing. So, duty cycle basically means that like how often do you think these red geysers are getting triggered? So if you just uh, think of the percentage or like the fraction, what am I saying? It's the fraction of red geysers you are seeing in the elliptical galaxies in a volume limited area, then you can transform that fraction to a time scale, like how often are you seeing. And
Okay.
on top of that, there is the other thing that you are seeing all these galaxies to have a spatial extent of the whole like manga bundle. So it's like 20 kiloparsec or something, and we see the velocity to be like 300 kilometer per second or something like that. So that just dividing that out gives you like a time scale of 10 to the 7 year or so. So that's a very like brute force way of doing it, and that kind of matches with like the minor merger rate that you see in the typical nearby galaxies around us. So that's like a very first order kind of answer.
Okay.
um uh and what was the other part that you were asking, the other time scale aspect?
I think you should move on to other questions, and I'll discuss this with you.
Okay,
Nice talk.
thank you.
So I think we can move on to SS sir's questions. Sir, please go ahead.
Well, Namrata, good, nice
Hello, sir.
talk, and that intrigued lots of questions.
I know
So,
I get criticism everywhere, so yeah, bring it on.
uh, I don't know whether it's criticism or anything. First thing is that about your motivation and the way you are trying to tackle it.
Mhm.
So you are looking for signature how to form the giant ellipticals.
uh
But
no, actually not. Maybe it's like the way I presented it. It's not like the transformation, or is it more like how the star
star
formation is
formation,
compressed in like massive elliptical? So these are already like elliptical. So these are not on the process of changing. These are
but
already.
process it's already elliptical. Okay,
Yes.
so you're trying to address how the quenching of the star
Right.
formation is happening.
happens in the later stage of the galaxy evolution.
The later stage of the galaxy evolution.
Yeah.
Okay, fine.
Yeah.
So regarding the question, so when you are talking about the kinematics,
Right.
okay, so
Mhm.
you are saying the velocity field matches with the whatever you are expected from the outflow thing. This outflow model
Uh-huh.
must have some kind of luminosity inherent to find that velocity field.
Yes. So um,
That
uh,
matches with radio luminosity, or it's what is that?
no. So this toy model is actually it's inspired from something called a Jeans anisotropic model or JAM modeling. If you have heard about it. So what this does basically, it takes the stellar photometry or the stellar light distribution in a galaxy. Let's say I am trying to match the velocity field with this galaxy. So I look at what's the stellar distribution in that galaxy. From that stellar distribution, you can create, and you also have the stellar kinematics. So you already know what the star. From that, you can estimate what's the gravitational potential created by the stars, and you can add a dark matter halo like NFW profile on top of it. So you have like a potential, right, that you can model from the stars. So then what you do is you just assume that that's the galactic potential, and then you estimate what's the maximum allowed velocity that you can have. The galaxy is rotating, is just rotating, so it's under the influence of the gravity. So yeah, when you have like the potential model, so you can just like figure out how far or how fast the gas is rotating in under that potential. And that is so that is basically what I was doing with the disk model, right? And here, so these are all like inspired from that JAM model. So we actually put the stellar kinematics and the stellar photometry here as the input, and you take the inclination, the axis, the
Yes,
PA, etc., etc. And then you also assume that the gas clouds that is in there, this tracks the ionization of the stars in the background. So for the evolved population, you generally assume the ionization to be solely from the post-AGB or other evolved stars. So your ionization, so it just follows the star, the background star, and that's it. So the stellar, it's just the potential.
no, that
yeah,
I understand that, but the conical thing, that is the wind
right,
model, correct?
yeah. So here
that should have certain energy input. That's what I'm saying.
Yeah, so that
to
does
have
not
that
have
velocity.
Yes, so that I said in the talk, that there is nothing like assumed in that with respect to the wind. It's just assumed that there are gas particles which is just moving radially outward, and they have like a
No, I'm
density.
just saying that, okay, I understand that, but I am having said that whatever, even if the kinetic energy of the thing that
Right.
is going to be giving you that that kind of velocity
Right.
flow,
Yeah.
is that comparable to your radio flux, or
Yes, so that is
it's
comparable from the data itself. So for that we don't need model. So yes, so we have yes. So from the data, the luminosity is something like, okay, I can just shift it. So the luminosity is around like the luminosity comes out to be like 10 to the 21 to 10 to the 22 watts per hertz, like the radio luminosity. And if you just convert that to the energy, the radio energy, that's like 10 to the 41 or 42 hours per second. And the kinetic energy of the wind, which you can just do half mv square divided by t, that's like 10 to the 39 or 10 to the 40 hours per second. So that is comparable. That just from the data, you don't need model for that. I think I misunderstood your question.
Oh, thanks.
Thank you, SSR. And with that, we can move to SC ma'am's question. So ma'am, please ask the question.
Okay, and Namrata, can you hear me?
Yeah.
Oh, actually, fantastic talk, wonderful talk. I also had multiple questions, but I'm going to ask a simple one right now because we also have the interaction session after this. Yeah, I actually had this question that what is the typical luminosity of your AGN sources,
Yeah. So
or
these
whatever your sources, and
Yeah,
you said it's 10 to the
yeah, I actually have a plot here. So this, so the red geysers are the red points. So these are average
yes.
like 10 to the 22. Do not go over 10 to the 23. These are the maximum. So these are mostly like the
So
lower part.
okay, but that's not very different from the red manga galaxies, right? The typical galaxies. I don't see that these red guys are very
So the
different
red
from.
manga galaxies are basically every galaxies in manga which are red and dead, like these are ellipticals, which are detected in radio.
In radio.
Yes,
So these
and
are all
these are
first.
mostly, yeah, so these are mostly the giant radio galaxies probably. And
Okay.
there are like a few low luminosity end.
Okay. So this is first detected, as you said,
Yeah,
right?
these are
all first
yeah,
detected.
yeah.
Now, my question is that suppose I believe your proposal, that these are low luminosity AGN.
Uh-huh.
Now, as we know that if we look at the AGN SED, they might be bright in other wavelengths also. So is
Right.
there a chance that this field has been observed, for example, in X-rays,
Yeah.
and you do an X-ray stacking or something and
Yeah.
see that if they could have X-ray counterparts?
Yeah, so that's actually a good question, because I have been wanting to see them in X-ray as well. So the problem is that we don't have, at least until Rosita like releases its data in public, we do not have X-ray data all over that, like that covers the entire SDSS sky.
That's right, but you can have, so yeah,
But then like what we generally do is like we take the red geyser sample and then we also take control sample and then we like match them. If you do not have coverage, how would you compare them?
I understand, but there is no survey where you have this. So there is no Chandra archival data or anything where you have the
I looked at Chandra data. Yeah, there is not a lot there. I have like, yeah, so I have like 160 or 170 red geysers right now in the current release of manga data. So I did that cross match initially when I had like fewer, and I didn't find a single one of them. I haven't done it with the new sample.
Okay, so please, others go ahead with the question, please. I think Argodeep had a question.
Yeah, Argodeep had a question. So the question is that for when you are doing the stacking analysis, how do you differentiate between the signal from the red geyser versus the control? Like, is it doing some statistically or manually? Like
How
visually,
do
I
you
think.
differentiate?
Yeah, I think the question is that, yeah, you showed a plot, right? That two images of the radio manga and radio red geysers and control. So how do you say that the red geysers have a higher radio signal compared to the control?
Oh, so we have a value.
Right.
Like we do an aperture photometry. So what we do is we have a stacked image. I cannot find that. Where is that?
Yeah, I guess I think the question is probably very simple. That is it a statistical detection or just a manual visual detection?
Right.
No.
So you showed that plot, right? Yeah.
Yeah. So this is, I just cannot find the plot.
No, it's actually much before. Yeah.
Yeah. So
right here.
Yeah. That's.
So yeah. So what we did is we have like the image, and then we also created something called blank stacks. So to kind of get a handle on the signal to noise, or to get a handle on the noise of this images. And then we do aperture photometry. So we basically just calculate the flux from that. And then we just, handle the noise, and then we compare the different samples. That is shown in the plot.
So next we have another question from Orithro. So the first question is that you talked about AGN having negative feedback on star formation, but it is often also sometimes said that AGNs can have positive feedback. So can red geysers have positive feedback on star formation?
Well, we haven't quite found that yet, because I think it's the way we select the galaxies. We always select from the red and dead elliptical population. We never really look at the star forming population at all. So we haven't, that is actually a good question. Like we have talked about whether there might be star forming galaxies that have red geysers, but they might not have the winds all the way to the entire extent of the galaxy, or they might haven't like really started their feedback action yet. So there might be some star formation, or there might be star formation due to their AGN activity themselves, as you were saying. But we haven't looked at the star forming sample at all. We have excluded anything that is star forming because of this very nature, because of this uncertainty, because of all this different activities going on. So yeah, we only look at non-star forming.
And also he had a small sub question, which is that since AGN is connected, outflows is connected to star formation rate, can star formation rate be used to determine some properties of AGNs like black hole mass and accretion rate?
So when I was saying about in this slide, actually, I was talking about the source of this radio, and then I was saying that about the star formation. So so star formation can actually give off radio emission. And so if you just back calculate, if you think that this radio is actually coming from star formation, then you can just like assume that, well, yeah, this is from a star forming glob, and then you can back calculate. But these are actually not coming from star formation, because the expected and the observed star formation rate doesn't match.
Right. So I think the question is more like this, that if you measure the star formation rate of a certain galaxy, can you tell anything about the black hole mass or the AGN in that galaxy?
So I don't think so, but because like the star formation rate, all of them is like, these are low, and we do not see any correlation. We haven't checked really, but maybe, I don't know. Maybe you can.
So these are not very star forming anyway. So
no, these are not very star forming. So those are all like pretty low. Yeah.
Okay. With that question, I think we will bring this session to an end. So thank you, Namrata, for the wonderful talk. And so we will have an extended